guys, so we're going to be talking about oxidation numbers, okay? Now, oxidation numbers are the same thing we've been talking about in terms of formation of anions and cations, where you're taking valence electrons and you're either losing or gaining some, and you're making positive and negative charges, which is an ion, on the atom. The positive or negative charge on an ion is written as a superscript, so kind of like an exponent. You form the following general pattern on the periodic table. Remember, D and F sublevels are called your group B elements, so they're not included when you talk about the pattern for oxidation numbers. We're only talking about those group A elements, which are representative elements, which are columns 1, 2, skip the middle section, and then 13 through 18. Those are called your representative group A elements. So when we talk about this trend, that's what we're referring to. So positive 1, positive 2, then you get over to column 13, positive 3, column 14, positive 4 or negative 4, depending upon what it's doing. Then you have negative 3, negative 2, and negative 1. The reason they are negative is because they're gaining electrons, because they are closer to the noble gas column, which is column 18. So what happens is they want to gain enough electrons to move over, whereas metals want to lose electrons to move down a row to become stable. Okay, this predicts the proportion of elements in a compound. So basically, how many elements are going to combine with another element depends upon their oxidation states. Okay, now when you're forming ionic compounds, they're composed of ions. Ionic compounds are electrically neutral. Okay, so what that means is the charges between the metal and the non-metal have got to equal 0. They've got to cancel out. So sometimes when this happens, you have to create more elements of either metals or non-metals so that these charges balance out. Now, you saw that when you did that little worksheet on formation of cations and anions. As you guys were drawing more atoms with the valence electrons, that's what you were essentially doing. You're forming ionic compounds. So with an ionic bond, they call these electrostatic forces, because electro meaning there's electricity, okay? So these charges, these ions, can produce electrical or conduct electrical current. So that's where the electrostatic comes into play. And it's these forces that hold ions together in an ionic bond, okay? They're called ionic bonds because what happens is this electron, so if you're making table salt, you have sodium, and when sodium strips that electron off of its nucleus, okay, or outer valence electron strips off and goes to the chlorine, that transition produces a positive sodium ion and a negative chloride ion. When this occurs, you're going to get a bond between the two, because remember, like charges repel and unlike charges attract. So what happens is this sodium ion is now attracted to the chlorine ion. So they form a bond, and that's how we get table salt, okay? Now, let's look at a couple of examples. Now, this should look familiar because this is what you just worked on when you were dealing with formation of cations and anions, okay? So you have calcium that has 2 outer electrons, 2 valence electrons, and you have a phosphorus which has 5. This phosphorus needs 3 electrons in order to be full, in order to have 8 outer electrons. But that one calcium can only donate 2 electrons. So it's kind of going back to the formation that we just did the other day. All the electrons must be accounted for, and each atom will have a noble gas configuration, which is stable, okay? So what are we going to do in this situation? Well, that calcium is going to give both of its valence electrons to the phosphorus, okay? And now it's going to get a +2 charge. Now, this phosphorus is going to be negatively charged, but it needs 1 more electron in order for it to be stable. So we're going to go out and find another calcium and strip that last electron it needs from that calcium, okay? So this should look familiar from the formation of cations and anions page, which you've already done, okay? Now your phosphorus has a -3 charge. However, now we've got this lingering electron over here on this other calcium. So now we're going to have to create another phosphorus. Now that calcium has a +2 charge, and then finally we're going to have to get another calcium in order to satisfy this phosphorus. Okay, and both of those are going to travel over here and land on that second phosphorus. So now we have 3 calcium atoms with a +2 charge and 2 phosphorus atoms with a -3 charge. So when we make our formula, and let me go back to that, okay? It takes 3 of these to cancel out 2 of these. Look at the charges. You have to equal 0. The whole purpose is your positive charge needs to be the same as your negative charge because you're trying to come out to the sum of 0. You're trying to cancel out these charges so that you're electrically neutral. So what happens is plus 2, plus 2, plus 2. All those together equal a plus 6. Phosphorus, a -3 and a -3, all together equal a -6. So a positive 6 and a -6 will cancel out. Now, when we write this as a chemical formula, you're going to drop your charges and you're going to write it with subscripts, okay? So how many calciums did we have here? 3. How many phosphorus did we have here? 2. So look at the next slide. 3 calciums, 2 phosphorus, okay? We write them at the bottom as subscripts. Now, you write with however many you had. So I had 3 calcium, so that's why I put a 3 here. I had 2 phosphorus, and that's why I put a 2 here. Now you've made what we call the formula for an ionic compound. And a lot of times it's referred to as what we call a formula unit, okay? Now, in formation of ionic compounds, okay, a chemical formula shows the kinds and numbers of atoms in the smallest representative unit of a substance, okay? A formula unit is the lowest whole number ratio of ions in an ionic compound, all right? So it's the lowest whole number ratio. Now, what are 3 properties of ionic compounds? So think about this. You know that they're bonding, they're going to form a tight bond, and unlike charges attract, there's a strong attraction between them. So what that means is that they are mostly crystal solids, so that's why they call them salts. So if you ever look at these salts up close, they're actually going to form crystals, okay? So if you look at table salt under a magnifying glass, it'll look like a crystal. So most of your ionic compounds are going to form crystals. They generally have high melting points, okay? Because of that attraction between the positive and negative charges, and there's a strong attraction there, there's also a case where it takes more energy to pull them apart. So once they get connected, once they bond together, there's going to be a tight hold with that electrostatic force. When that happens, it's harder for those bonds to be broken. So when you actually melt a substance or dissolve a substance, you're actually breaking those bonds into positive and negative charges. So what happens is, in order to melt that, it's going to have a higher melting point because it's going to take more energy to break that bond, okay? And last, ionic compounds can conduct an electrical current, okay? The reason is you've got a metal and a non-metal bonding together, but the main reason is because you're going to have these ions floating around inside solution. So when you take an ionic compound and you put it in water and dissolve it, it breaks up into its ionic form. So it's going to have positive and negative charges. So if you actually took leads and stuck them in there, they would actually light a light bulb, okay? Most ionic compounds do consist of metals and nonmetals. The metal's written first, the nonmetal is written second, okay? So when you're looking at an ionic compound like table salt, sodium's a metal, chlorine's a nonmetal. So it's going to go in that order, metal and nonmetal. So here's an example of an aqueous solution. Okay, a molten solution means it was melted down. Okay, it has water in it. That's what makes it aqueous. And as you can see, this is table salt, right? So when table salt is dissolved and made salt water, that's why salt water conducts an electrical current. You've got your metal leads, electrodes in here, and then you're connecting it to a power source. And what happens is it's going to give the current meter, the voltmeter, it's going to give a reading. Or you could attach a light bulb here and it would actually light the light bulb, okay? But when you dissolve it, you've got these free flowing of sodium ions and chloride ions floating around in solution, and that's what's conducting the electrical current. Okay, now, there's 2 things that we're going to be talking about today, naming and writing ionic compounds. I just showed you how to write an ionic compound, how you form those, okay? Now we're going to talk about how did we get these names? How do we name ionic compounds? Well, there was a French chemist known as Antoine Lavoisier. Okay, he determined the composition of many compounds and found that it was becoming impossible to memorize all unrelated names of the compounds. So he worked with other chemists to develop a systematic method for naming chemical compounds. Their work is the basis for the system that we use today. Okay? So, when you're naming binary ionic compounds, binary means two elements. Okay? So, monatomic ions consist of a single atom with a positive or negative charge. Okay? So, we're looking at singular elements that have positive and negative charges. Only singular. That's why they're called monatomic. Binary means two. That means you're going to have a metal bonded with one metal bonded with one nonmetal. Okay? So, monatomic ions consist of a single atom with a positive or negative charge resulting from the loss or gain of one or more valence electrons, respectively. An anion name starts with the stem of the element and then the name ends in IDE. Remember how we talked a little bit about this when we were forming anions. We talked about halide ions, about how fluorine becomes fluoride, chlorine becomes chloride. So all of your negatively charged ions, your anions, will actually change the ending of their name to IDE. So oxygen becomes oxide, sulfur becomes sulfide, phosphorus becomes phosphide, and so on and so on. So all of these negative ions are going to become I's when you are naming, okay? Now, here's just a list of some of the group 1A, 2A, and 3A elements. So here you have your metals that are positively charged. You have lithium, sodium. Now, notice their names don't change. It's just the anions that change their name. So even in ionic form, your metals will keep their original name, okay? Then you have your nonmetals here, okay? Nitrogen becomes nitride, phosphorus becomes phosphide, and so on, as you can see, some of those general names for the elements, okay? Now, to name a compound that contains two elements, first thing you're going to do is identify the cation. The first element listed is going to be your cation, and then you identify the anion, okay? So your steps are, you identify the cation and anion. Then you name the cation by its element name. Step 3, name the anion by changing the last part of its element name to IDE, okay? And then finally, you write the name of the cation first and the name of the anion second, okay? So here's an example. So if I have Ba plus 2, okay, that's just going to be barium, okay? Then you have aluminum, and then you have potassium. And as you can see, okay, Ba plus 2 stays barium. Aluminum stays aluminum. All of your positive ions don't change. K stays potassium. But when you get your anions, this is where they're going to change. So nitrogen changes to nitride. Oxygen changes to oxide. Fluorine changes to fluoride, and so on and so on. So here is an example of how your anions will change their name to IDE. Okay? All right, so let's name the following, write the names of the following compounds. So the first one listed, you have Ca. So if you look that up on the periodic table, that's calcium. And O is oxygen, but remember, it's an anion. So the second element is your anion, so we're going to change that to oxide. So for the first one, you're going to have calcium oxide. Second one, you're going to have potassium bromide. Third, you're going to have aluminum oxide. And then finally, you're going to have magnesium chloride. So as you can see, naming is fairly easy. You're just looking for the element on the table, naming it, and it's the second element listed, that's your anion, and you're just going to change it to IDE, okay? Now, writing formulas is going to be a little more difficult, okay? So when you're writing formulas, you have to remember the charges have to cancel, have to equal 0. So if I look here, and I look at my sodium here, okay? That's a +1. Bromine is a -1, okay? So when I make that, these two are going to cancel out, and you're going to end up with NaBr, okay? Now the next one, I have Na plus and S -2. So it's going to take 2 sodiums to cancel 1 sulfur out. So when I do this, I'm going to have to write Na2S. +1, -3. As you can see, that's not going to cancel out. So it's going to take 3 positives to cancel out 3 negatives. So that means I need 3 sodiums to cancel 1 nitrogen out. So when I write that one, it's going to be Na3N. Okay? If I were naming them, it would be sodium bromide, sodium sulfide, sodium nitride, aluminum bromide, aluminum sulfide, and aluminum nitride. Okay? Now, that's what we're going to focus on in today's video. I'm going to send a sheet to you, and all you're going to do on that sheet is focus on naming ionic compounds. Okay? Then I'm going to come with another video where we're going to talk about just writing the formulas for the ionic compound. So I'll see you in a little bit, and I'll have a sheet for you for the naming, and you'll be working on that today. And then tomorrow we're going to do some more notes where we talk about writing the formulas, and then you guys will write your formulas. Okay? Thank you.